It's kind of wild to think about. What if one of the most powerful and terrifying forces we've ever known didn't start in a lab, but is just an idea in ancient Greece? Well, that's exactly what happened. This is the story of the atom, and it's a journey from a simple, indivisible idea to an absolutely world-changing power.
So let's start our story not at the beginning, but actually near the end. It's 1940. Two physicists, who are refugees from Nazi Germany, hand this memo to the British government. And what's so chilling is the language. It's so calm, so clinical. They're not just describing a bigger cannon. They're talking about something totally new, a super bomb.
And what did a super bomb even mean? It meant creating, just for a split second, a temperature as hot as the inside of the sun. And the source for all that power? Just about a pound of uranium. I mean, think about that. Unimaginable power all locked up inside a rock you could hold in your hand.
So that's the big question, right? How in the world did we get here? How did humanity go from just a philosophical concept to unlocking this incredible, frankly terrifying secret that was hidden inside matter itself? Well, to answer that, we have to go way back. Okay, the first part of our story doesn't happen in some high-tech lab with blinking lights. Nope, it takes place entirely inside the minds of ancient philosophers.
So let's hit the rewind button. We're going back 2.5 millennia, all the way to ancient Greece. This was a time of pure logic, reason, and these amazing thought experiments.
A philosopher named Democritus asked this really simple question. What happens if you just keep cutting something in half, over and over again? He figured, logically, you have to eventually get to a particle that's so small you just can't cut it anymore. He called this atomos, which literally means indivisible. What's so amazing is that this wasn't science. It was pure philosophy. No experiments, no proof. And yet, the core idea that everything is made of these fundamental little particles was just astonishingly right.
So for about 2,000 years, the atom was just an idea. A good idea, but still just an idea. But then the age of chemistry kicked off, and the hunt for actual, solid evidence was on. And then things started moving fast. In just a little over 100 years, our picture of the atom went from this fuzzy concept to a really detailed model. As you can see here, it happened in a series of just breathtaking leaps. And each discovery didn't just build on the last one. A lot of times, it completely flipped what we thought we knew on its head. The first real proof came from John Dalton in 1808. He noticed something really cool. Elements always combine in simple whole number ratios. Like, look at this copper oxide. For every 100 parts of copper, you get 12.5 parts of oxygen. But in another type of copper oxide, you get exactly double that, 25 parts. That's not random. It's behaving as if matter is made of these discrete little blocks, atoms, that are combining in these simple, predictable ways. The atom had finally made it into the lab.
But what did this atom actually look like? Well, in 1897, J.J. Thomson discovered this tiny negative particle called the electron. So he pictured the atom as a sort of plum pudding, a ball of positive charge with these negative electrons just stuck in it. But his student, a guy named Ernest Rutherford, decided to test this. He fired these tiny positive particles at a super thin sheet of gold foil, fully expecting them to just punch right through the pudding. But what happened next absolutely shocked him. A few of the particles bounced right back. Rutherford's famous quote here just perfectly captures how stunned he was. The only possible explanation was that all the atom's positive charge and almost all of its mass were crammed into this impossibly tiny, dense core, a nucleus, which meant the atom, it was mostly empty space. Wow. Okay, but Rutherford's model had a huge problem. According to the physics of the day, those orbiting electrons should lose energy and just spiral right into the nucleus, meaning all matter should just collapse instantly. Whoops. The answer came from this weird new field called quantum theory. A physicist named Niels Bohr came up with a radical idea. What if electrons can only exist in specific energy levels, or shells, like planets locked in very specific orbits? They can jump between shells, but they can't exist in between. This totally solved the collapse problem, and here's the bonus. It also perfectly explained why different elements glow with their own unique colors when you heat them up.
So the picture was getting a lot clearer, but the very heart of the atom, that tiny nucleus, it was still hiding a pretty big secret.
Say physicists could measure the positive charge of the nucleus, and they knew that charge came from particles they called protons. But when they measured the nucleus's mass, it was almost always way heavier than just the protons could account for. There had to be something else in there. What was it?
And in 1932, another one of Rutherford's students, James Chadwick, he found it. The answer was the neutron, a particle with about the same mass as a proton, but with no electrical charge at all. It was the missing puzzle piece, the thing that accounted for all that extra weight in the nucleus.
And the neutron, oh man, it turned out to be so much more than just extra weight. Its lack of charge made it the perfect tool for exploring the atom's core. Think about it. Because it's neutral, it isn't pushed away by the positive charge of the nucleus. You could fire a neutron straight into an atom's heart. It was the key that was finally going to unlock the nucleus's immense, and I mean immense, power.
So the discovery of the neutron kicked off this chain of events that would take the indivisible atom and do the one thing its name said you couldn't do: split it.
I mean, just look at how quickly things accelerated. It was just 6 years after the neutron was discovered that scientists in Germany started bombarding uranium with these perfect bullets. They were absolutely floored when they found they'd created much lighter elements. They had actually split the atom. It took Lise Meitner and her nephew Otto Frisch, who were both refugees from that same regime, to explain what was happening. They gave it a name: nuclear fission. And in that moment, the world changed forever.
Now here's the truly world-changing part of the discovery. When a uranium atom split, yeah, it released a ton of energy, but it also kicked out more neutrons. And what do those neutrons do? Well, each one can go and split another atom, which releases even more neutrons, which go on to split even more atoms. You see where this is going, right? It's a self-sustaining, explosive process. That's the chain reaction. It's the engine that powers both a nuclear reactor and an atomic bomb.
And this brings us right back to where we started. That 1940 memo wasn't what if anymore. It became the blueprint for the Manhattan Project. It kicked off an atomic arms race, leading to that first test in the New Mexico desert in 1945, and then, of course, the bombs dropped on Hiroshima and Nagasaki.
So after this incredible journey, what's the big takeaway? For me, it's a perfect example of how science really truly works. It's not some big book of unchanging facts. It's a process. Each model, from Democritus's simple little ball to Bohr's mini solar system, it was the best possible explanation they had with the evidence at the time. And when new evidence came along, the model changed. Science works not because it's always right, but because it's willing to be wrong and to get better.
And that flexibility, that malleability, leaves us with one final, really vital question. This 2,500-year quest for knowledge gave us a power of both creation and destruction on a scale we had never imagined. The scientific journey got us into the atomic age. The real question for us today is, where can it take us next?